Look up at the night sky, past the scattered stars. Beyond the familiar constellations, what you're seeing is just the tiniest glimpse of an unfathomable cosmic tapestry. Galaxies, those colossal islands of stars, gas, and dark matter, stretch across the universe in numbers so vast they defy comprehension. But here's the thing. Even if you've spent years marveling at space documentaries or flipping through astronomy books, the truth about galaxies is far stranger, wilder, and more mysterious than most of us realize. What if I told you some galaxies are cannibals, devouring their neighbors in slow-motion cosmic feasts, or that others spin like celestial whirlpools, hurling stars across space at speeds that would make light itself dizzy? The universe doesn't just hide these secrets, it flaunts them in plain sight, waiting for us to piece together the clues. Think about this. Our own Milky Way, a sprawling spiral of hundreds of billions of stars, is just one drop in an ocean of galaxies, each with its own quirks, tragedies, and mind-bending physics. Some galaxies are so ancient they formed when the universe was barely a toddler, their light taking billions of years just to reach our telescopes. Others are cosmic ghosts, invisible to our eyes yet detectable through their gravitational whispers. And then there are the rogue galaxies, flung from their clusters into the void, destined to wander the darkness alone. These aren't just abstract concepts, they're the dramatic, almost poetic stories written across the cosmos, and they're unfolding right now, whether we're watching or not. That's why today we're diving deep into the enigma of galaxies, uncovering 30 facts so astonishing they'll make you question everything you thought you knew about the universe. From galaxies that shouldn't exist according to our current laws of physics, to black holes so powerful they sculpt entire galactic neighborhoods, these revelations will leave you equal parts awestruck and humbled. So buckle up, this isn't just a tour of the cosmos. It's a front-row seat to the most spectacular, bizarre, and downright unbelievable phenomena the universe has to offer. Ready to have your mind blown? Let's begin. Here's something that might shatter your cosmic expectations. When galaxies collide, it's nothing like a Hollywood disaster movie. Picture two massive spiral galaxies, each containing hundreds of billions of stars, slowly drifting toward each other over billions of years. You'd think their stars would crash like cars in a cosmic pileup, right? But the reality is far stranger. Despite the mind-bending scale of these mergers, individual stars almost never collide. Why? Because space is overwhelmingly, incomprehensibly empty. Let's break it down. The average distance between stars in a galaxy is about 4 to 5 light-years. That's roughly 25 trillion miles. To put that in perspective, if our sun were the size of a grain of sand, the next closest star would be another grain over 4 miles away. Now imagine two galaxies merging, each with that same absurd emptiness between their stars. The odds of any two stars physically hitting each other are astronomically low. Instead, what really happens is a slow, gravitational dance, galaxies stretching and warping each other like taffy, their stars gently tugged into new orbits without ever getting close enough to touch. Take the Milky Way and Andromeda, for example. Right now, they're racing toward each other at 250,000 miles per hour, set to collide in about 4.5 billion years. But when they do, not a single star will likely smash into another. Instead, gravity will twist both galaxies into a chaotic new shape, flinging some stars into intergalactic space while others settle into a giant elliptical galaxy nicknamed Milky. The real fireworks won't be stellar collisions, it'll be the gas and dust between stars slamming together, triggering bursts of new star formation in dazzling, fiery ribbons. So while galaxy mergers might sound violent, they're more like a cosmic ballet, graceful, inevitable, and strangely quiet. The universe doesn't do destruction for drama's sake. It rewrites the sky with patience, gravity's invisible hand weaving new patterns across billions of years. And somewhere in that distant future, if any civilizations are left to watch, they'll witness not a catastrophe but a rebirth, a reminder that even in the vastness of space, change is the only constant. We might think of the Milky Way as one of a kind, a cosmic masterpiece with its elegant spiral arms and glowing core, but out there, hidden among the billions of galaxies, it has an almost perfect twin. Meet UGC 12158, a galaxy so strikingly similar to ours that astronomers do a double take when they see it. From its sweeping spiral structure to its bright central bulge, this distant neighbor mirrors our galactic home with uncanny precision, sitting roughly 400 million light-years away in the constellation Pegasus. What makes this discovery so thrilling isn't just the resemblance, it's the window it gives us into our own galaxy's past and future. Since we're stuck inside the Milky Way, we can't step back and see its full shape, like trying to map a forest while standing in the middle of it. But UGC 12158, that's our cosmic mirror. By studying its structure, star formation patterns, and even the way its spiral arms twist, astronomers can piece together clues about how the Milky Way evolved over billions of years. Here's where it gets even more fascinating. UGC 12158 isn't just a static lookalike. It's actively forming stars at a rate similar to our galaxy, with pockets of glowing gas and young, blue stars scattered along its arms. This suggests that, like the Milky Way, it's had a relatively quiet cosmic life, no dramatic collisions or violent encounters to disrupt its delicate spiral. That calm history makes it a perfect benchmark for understanding how spiral galaxies like ours mature without catastrophic interruptions. But the similarities don't end there. Both galaxies host supermassive black holes at their cores, though UGC 12158 is slightly more active, sending out faint ripples of energy. By comparing the two, scientists can explore how these gravitational monsters influence their galaxies over time, whether they stifle star formation or trigger it, and how their outbursts shape the surrounding space. It's like finding a living blueprint of the Milky Way, one that lets us test theories about our own galaxy's fate without waiting billions of years to see it unfold. So the next time you gaze up at the Milky Way's faint band of light, remember, somewhere out there, its twin is spinning in the darkness, holding secrets to our past and maybe even hints about our future. And as telescopes grow more powerful, this cosmic doppelganger will keep teaching us just how ordinary and extraordinary our galactic home really is. Not all galaxies blaze with the fiery birth of new stars. Some are cosmic graveyards, massive, ghostly cities where star formation ceased billions of years ago. These red and dead ellipticals drift through space like frozen relics of a more vibrant past, their crimson glow betraying the aging populations of stars slowly burning out. Unlike our Milky Way, where nurseries of gas and dust spark new stellar generations, these galaxies are eerily quiet, their gas supplies exhausted or stolen away. One of the most famous examples, Messier 87, the colossal elliptical galaxy at the heart of the Virgo cluster. Its yellowish hue tells the story. No young blue stars, just ancient red giants lumbering toward their final act. But how does a galaxy, a system teeming with potential, just stop? The answers lurk in the destructive power of supermassive black holes. At the core of many dead ellipticals, these gravitational beasts rage against their own galaxies. When they feed on surrounding matter, they unleash torrents of energy that heat up or blast away precious star-forming gas. Imagine a wildfire scorching a forest before new seeds can take root, except here, the flames are jets of plasma screaming across thousands of light years. But black holes aren't the only culprits. Some galaxies simply starve to death. In dense galaxy clusters, the space between galaxies isn't empty, it's filled with superheated gas. When a galaxy plows through this environment, the pressure strips away its cool gas, the raw material for new stars, like a cosmic wind tearing at a dandelion. Over time, the galaxy exhausts its reserves, left with nothing to fuel stellar birth. Others might have burned through their gas too quickly in a frenzy of early star formation, leaving behind nothing but the embers of aging stars. What's haunting is that our Milky Way could one day join their ranks. As galaxies age and environments shift, even the most vibrant spirals may eventually fade into red and dead ellipticals. It's a reminder that the universe has its own life cycles, grand, slow, and utterly indifferent to the flickering lives of stars. These silent giants aren't failures, they're milestones in the epic story of cosmic evolution, holding clues to how galaxies live, die, and sometimes, against all odds, find ways to reignite. If our Milky Way feels vast at 100,000 light-years across, wrap your mind around this. The largest known galaxy, IC 1101, spans an almost incomprehensible 16 million light-years from end to end. That's 160 times wider than our home galaxy, a leviathan so enormous it could swallow the entire local group of galaxies, including Andromeda, and still have room to spare. How does a galaxy grow to such monstrous proportions? The answer lies in a history of cosmic cannibalism. IC 1101 sits at the heart of the Able 2029 galaxy cluster, a crowded metropolis of thousands of galaxies. Over billions of years, its gravity has acted like a cosmic vacuum cleaner, pulling in smaller galaxies and merging with them, growing larger with each collision. Picture a snowball rolling downhill, gathering more mass with every revolution, except here, the snowball is a galaxy, and the hill is the relentless pull of gravity across eternity. The Milky Way, by comparison, has had a relatively peaceful existence with only a handful of minor mergers in its past, but IC 1101, it's the product of dozens, perhaps hundreds of galactic mergers, each one adding stars, gas, and dark matter to its already staggering bulk. These collisions don't just increase its size, they fundamentally reshape it. Spiral galaxies like ours have delicate, rotating arms, but repeated mergers smear and scramble those structures, leaving behind a featureless, football-shaped elliptical galaxy. That's why IC 1101 looks nothing like the Milky Way. It's a blended behemoth, the end result of a chaotic construction project spanning the age of the universe. But here's the twist: despite its mind-boggling scale, IC 1101 isn't as densely packed as you might think. Its stars are spread thinly across its enormous volume, giving it a ghostly, diffuse glow. If you stood on a planet inside it, the night sky wouldn't blaze with stars instead. They'd be few and far between, like distant streetlights in an endless city. That's the paradox of supergiant galaxies. They're vast yet hollow, their grandeur diluted across unimaginable distances. Even more fascinating, IC 1101 might not hold its title forever. As astronomers peer deeper into the cosmos, they're finding ever larger structures, hinting that this record breaker could one day be dethroned. But for now, it stands as a titan, a testament to the universe's ability to build monuments of staggering scale, one galactic merger at a time. Imagine a star not just drifting lazily through space, but screaming across the cosmos at speeds topping 2 million miles per hour. These aren't rogue stars born in the void. They're hypervelocity stars, celestial projectiles violently ejected from their home galaxies. The force behind this cosmic slingshot, a dance with destruction at the edge of a supermassive black hole. Picture a binary star system, two stars orbiting each other, wandering too close to the galactic center where a black hole lurks. As gravity pulls one star toward oblivion, the other gets whipped around like a stone in a sling, gaining tremendous speed before being hurled outward. This isn't a gentle nudge. The surviving star rockets away with so much energy it completely escapes the galaxy's gravitational grip. Some of these exiles reach velocities so extreme they'll eventually leave the galaxy cluster entirely, doomed to drift through intergalactic space forever. The first hypervelocity star discovered, imaginatively named S5HVS1, was clocked at over 1.5 million miles per hour, fast enough to cross the entire United States in less than 2 seconds. But speed isn't the only astonishing part. These stars carry secrets about the galaxies they fled. By tracing their paths backward, astronomers can map the invisible gravitational landscape near supermassive black holes, areas too chaotic to observe directly. Here's what's even wilder. Not all hypervelocity stars come from black hole encounters. Some might be flung outward by supernova explosions, where a dying star's violent death kick sends its companion racing into the void. Others could be refugees from ancient galaxy collisions, where the gravitational chaos of merging systems sent stars careening in all directions. The universe is constantly rearranging itself, and hypervelocity stars are proof, celestial shrapnel from the most extreme gravitational events imaginable. As they streak through the cosmos, they remind us that even in the vast, seemingly serene expanse of space, there's no such thing as a quiet corner. We often hear the universe is vast, but that word doesn't begin to capture the truth. Consider this: there are more galaxies in the observable universe than grains of sand on every beach, every desert, every inch of Earth's coastline combined. Hubble's deep field surveys suggest the number hovers around 2 trillion galaxies, each one a swirling metropolis of stars, planets, and mysteries. To wrap your mind around that, imagine holding a single grain of sand between your fingers. Now picture it as a galaxy glittering with billions of stars. Now scatter enough grains to fill an Olympic-sized swimming pool. That's just a fraction of what's out there. The scale is so staggering it defies human intuition. If you tried counting every galaxy at a rate of 1 per second, it would take you 63,000 years just to reach 1 trillion, and you'd still have another trillion to go. And here's what's even wilder: that 2 trillion is likely an underestimate. Our telescopes can only peer so far into the cosmic fog, and as technology advances, that number could grow. Some theorists suggest the true count might be 10 times higher, with countless dwarf galaxies lurking in the shadows, too faint to detect. Think about what this means for the universe's architecture. If each galaxy were a single pixel on a screen, you'd need a display the size of a stadium to render them all. And yet, despite this unfathomable sprawl, galaxies aren't randomly scattered. They cluster into filaments and walls, forming a cosmic web spanning billions of light years. Picture foam on ocean waves. The galaxies cling to the fragile edges of bubbles with vast, empty voids between them. This isn't just a fun fact, it reshapes our understanding of existence. With so many galaxies, the odds of life, or even other civilizations, feel less like a fluke and more like a certainty. Somewhere in that unthinkable number, there might be a galaxy where beings are staring up at their sky, wondering if they're alone, just like us. The universe didn't just build a home for humanity, it built 2 trillion of them. And we've barely begun to explore. The Milky Way isn't the flawless spiral we often picture. It's warped, twisted like a potato chip at the edges. Recent observations reveal our galaxy's outer disk isn't flat at all. It bends upward on one side and downward on the other, creating a subtle but unmistakable S-shape when viewed from the side. This cosmic contortion isn't unique. Many galaxies show similar warping, but the fact that our own home bends this way forces us to rethink its history and the forces shaping it. So what's bending an entire galaxy? One leading theory points to an ancient collision. Around 3 billion years ago, a smaller galaxy, possibly the Sagittarius dwarf, may have plowed through the Milky Way's outskirts. Like tossing a pebble into a pond, the gravitational ripples from that encounter could have sent waves through our galactic disk, leaving it permanently distorted. But there's another, more mysterious culprit: dark matter. The invisible halo surrounding our galaxy isn't perfectly symmetrical. Its uneven tug might slowly twist the outer stars over time, like an unseen hand warping a vinyl record left in the sun. Here's where it gets even stranger. The warp isn't static, it moves. Imagine spinning a slightly bent frisbee. The warp rotates around the galactic center, completing a full cycle every 600 to 700 million years. Stars on the outer edges don't just orbit the core, they bob up and down through the warped plane like horses on a carousel. This motion leaves traces in the data, subtle shifts in starlight that advanced telescopes like Gaia are now mapping with unprecedented precision. What does this mean for us? Surprisingly little Earth sits safely in the flatter inner region, far from the warped chaos at the edges. But for astronomers, this twist is a gold mine. By studying how the warp moves and evolves, they can reverse engineer the Milky Way's violent past, testing theories about those long-ago collisions or the distribution of dark matter. It's a reminder that even after centuries of observation, our galaxy still holds puzzles once written in the slow, silent bending of stars. Next time you gaze at the Milky Way's glowing band, remember, you're looking at a cosmic pretzel, its shape whispering secrets about forces we're only beginning to understand. Most galaxies blaze with stars, their spirals and disks glowing across the cosmic stage, but some lurk in the shadows, nearly invisible to our eyes. Take Dragonfly 44, a galaxy so faint it was only discovered in 2015. From a distance, it looks like a wispy smudge, a ghostly patch of light barely distinguishable from the blackness around it. Yet despite its feeble glow, this cosmic spectre holds staggering mass, rivaling our Milky Way. Here's the twist: less than 1% of that mass comes from stars. The rest, an unfathomable halo of dark matter, the universe's most enigmatic substance. How does a galaxy like this even exist? Conventional models suggest galaxies form when dark matter's gravitational pull gathers gas, which then condenses into stars. But Dragonfly 44 flips that script somehow. It collected just enough gas to birth a handful of stars, leaving its dark matter skeleton almost entirely exposed. It's like finding a city where skyscrapers should be, but instead there's only scaffolding, hauntingly empty. This raises a baffling question. Did something stifle its star formation, or was it born this way, a cosmic experiment gone quiet? The discovery of these dark galaxies forces astronomers to rethink the rules. For decades, we assumed dark matter was the hidden foundation of visible structures. Now we're finding entire galaxies where dark matter didn't just stay in the background, it took center stage, leaving starlight as a mere afterthought. Some theories suggest these galaxies might be failed giants, where supernova explosions or ravenous black holes blasted away their gas before more stars could ignite. Others propose they're remnants of ancient collisions, stripped of their stellar populations by violent encounters. What's certain is this: the universe crafts galaxies in ways we're only beginning to grasp. Dragonfly 44 and its invisible kin aren't flukes. They're clues whispering that our cosmic neighborhood holds far stranger residents than we ever imagined. And as telescopes grow more sensitive, we'll likely find more of these phantoms, silent, shadowy, and utterly rewriting the story of how galaxies live and die. We tend to think of galaxies having just one supermassive black hole at their core, a single gravitational monarch ruling from the center. But nature loves breaking our expectations. Some galaxies, especially those born from violent cosmic mergers, end up with two or even more supermassive black holes circling each other in a slow, inevitable dance. Take NGC 6240, a tangled wreck of a galaxy 300 million light-years away. It doesn't just have one black hole, it has three, each weighing millions of times the mass of our Sun, trapped in a gravitational standoff that will last for millions of years. How does this cosmic clutter happen? When two galaxies collide, their black holes don't immediately merge. Instead, they sink toward the new galaxy's center, drawn together by gas and starlight friction. But space is so vast that even these titans take ages to find each other. For eons, they orbit as a binary pair, sometimes with a third black hole joining the chaos if another merger occurs. The process is messy, flinging stars out of the galaxy and warping entire regions of space-time with their gravitational pull. The energy these dueling black holes release is almost beyond comprehension. As they spiral closer, they rip apart clouds of gas, creating frenzied regions of star formation and spewing jets of plasma at near-light speeds. The environment around them becomes so extreme that atoms are torn apart, and space itself vibrates with gravitational waves, ripples predicted by Einstein and now detectable by observatories like LIGO. NGC 6240's trio of black holes, for example, will eventually collide in a cataclysm so powerful it will shake the fabric of the universe, sending gravitational waves echoing across billions of light years. But here's the catch: most binary black holes stall. Once they get within a few light years of each other, they run out of nearby stars and gas to steal energy from, leaving them stranded in a near-endless orbit. Astronomers call this the final parsec problem. It's why we don't see more black hole mergers despite the universe's violent history. Only in the densest galactic cores, where a third black hole or a massive gas disk can nudge them closer, do they finally unite. When that happens, the resulting merger can fling the newborn black hole clear out of its galaxy. A gravitational recoil so strong it turns the universe's most monstrous objects into cosmic outcasts. These multi-black hole systems aren't just cosmic oddities, they're time capsules. By studying them, we piece together the Milky Way's own violent past. Our galaxy's quiet central black hole suggests it hasn't had a major merger in billions of years. But one day, when Andromeda crashes into us, their black holes will begin this same slow tango, offering future civilizations, if any are left, a front-row seat to the most awe-inspiring collision imaginable. Until then, galaxies like NGC 6240 remind us that even the darkest corners of space are anything but still. Long before majestic spirals like the Milky Way dominated the cosmos, the universe's first galaxies were scrappy, hyperactive toddlers, tiny but ferocious. Astronomers call them blueberries, not for their size, but for their intense blue glow, a telltale sign of rampant star formation. These primordial dwarfs were only 1% the mass of our galaxy, yet they churned out stars at rates that would put modern galaxies to shame, igniting hundreds per year compared to the Milky Way's sedate 1 or 2. What made these early galaxies so explosively productive? The young universe was a different playground, denser, hotter, and swimming with pure hydrogen and helium gas, the perfect raw materials for rapid star birth. Without heavier elements to cool the gas efficiently, it collapsed into stars in frenzied bursts, lighting up these compact galaxies like cosmic firecrackers. Imagine a fireworks factory the size of a garage pumping out endless sparks. That was the norm 13 billion years ago. The Hubble and James Webb Space Telescopes have spotted these blueberry galaxies at the edge of observable time, their light stretched and reddened by the expanding universe. But when astronomers adjust for that cosmic redshift, the original view emerges, searing blue hues from countless young, massive stars burning bright and dying young. These stars didn't just twinkle, they lived fast, exploded violently, and seeded the cosmos with heavier elements, paving the way for future galaxies to grow richer and more complex. Here's the kicker: despite their ferocity, these galaxies were fragile. Their small size made them vulnerable to ultraviolet radiation from neighboring starbursts, which could strip away their gas and stunt their growth. Many likely ended their lives as faint, star-deprived dwarfs or were cannibalized by larger galaxies emerging around them. Yet their legacy is undeniable. Every massive galaxy today, including our own, owes its existence to these tiny powerhouses that turned the early universe from a dark, featureless void into a canvas of light. They prove that in cosmology, as in life, the smallest things often pack the most transformative punch. Galaxies might seem like eternal engines of star creation, but some hit an off switch, starving themselves of the very material needed to spark new stellar life. This process, called quenching, turns vibrant, star-forming galaxies into quiet, aging relics, and it happens through some of the universe's most violent acts of self-sabotage. Take supernova, for example. When massive stars explode, they don't just vanish, they unleash shockwaves that heat surrounding gas to millions of degrees, pushing it out of the galaxy like a cosmic hurricane clearing debris. Over time, these repeated explosions can sweep a galaxy clean of cool gas, leaving nothing behind to form new stars. It's like a farmer burning their own fields, ensuring nothing can grow again. But supernova aren't the only culprits. Supermassive black holes play an even more dramatic role. When these monsters feast on gas and dust, they don't just swallow it quietly. They belch out torrents of energy in the form of jets and radiation. These outbursts act like galactic blowtorches, heating gas to such extreme temperatures that it can't condense into new stars. In some cases, the force is so intense it catapults gas clear out of the galaxy entirely. Picture trying to light a candle in a wind tunnel. That's what star formation faces when a black hole rampages at the heart of a galaxy. Astronomers have seen this in action with galaxies like M87, where jets from its central black hole stretch for thousands of light years, actively stifling star birth in their paths. Quenching isn't always quick, though. Some galaxies experience strangulation, a slower, more insidious process where they're cut off from fresh gas supplies. This often happens in dense galaxy clusters, where the space between galaxies is filled with scorching hot plasma. As a galaxy moves through this environment, its cool gas is stripped away like leaves in a gale, leaving it to exhaust its remaining reserves over billions of years. Without new gas flowing in, star formation sputters out, and the galaxy gradually transitions from blue and vibrant to red and dead. The eerie part, our Milky Way, may be on this path. While still actively forming stars, studies suggest its star formation rate has dropped significantly over time. Whether from supernova, black hole feedback, or simply running out of gas, even our galaxy isn't immune to the universe's quiet closing act. Quenching reminds us that galaxies aren't static, they're dynamic systems with life cycles, and sometimes their greatest threats come from within. At the heart of our Milky Way, hidden behind thick curtains of dust and stars, lurks a monster, Sagittarius A, a supermassive black hole with the weight of 4 million suns crammed into a space smaller than our solar system. Its discovery wasn't some grand eureka, a moment, but a decades-long detective story. Astronomers first noticed something strange in the 1930s when radio waves emanated from the galactic center, but it wasn't until the 1970s that they pinpointed the source, an intense, compact radio signal they named Sagittarius A. The star, or rather, a star in the Sagittarius constellation. It took another 30 years of tracking stars whipping around an invisible point at mind-bending speeds to confirm the terrifying truth. Something with unimaginable gravity was pulling the strings. What's fascinating isn't just its existence, but how oddly peaceful it is. Most supermassive black holes are messy eaters, tearing apart gas clouds and stars with such violence they outshine entire galaxies. But Sagittarius A, it's practically fasting. The amount of material it consumes is so puny that its emissions are a faint whisper compared to behemoths like the one powering quasar-ton 618. Some scientists joke it's on a cosmic diet. The reason might lie in its environment. While it has plenty of stars orbiting nearby, there's surprisingly little gas falling into its maw, just enough to produce occasional flickers of X-rays, like a distant campfire struggling to stay lit. Yet don't let its quiet demeanor fool you. In 2019, the Event Horizon Telescope collaboration unveiled the first ever image of a black hole's shadow. Not Sagittarius A, but its cousin in Messier 87. The Milky Way's own singularity was too active during observations, its turbulent surroundings making it harder to capture. That's the paradox of our galactic center. It's calm by black hole standards, but still capable of sudden, violent flares. In 2021, astronomers caught one such outburst, a burst of X-rays 3 million times brighter than normal, possibly from a wayward asteroid or gas cloud meeting its doom. Sagittarius is more than just a curiosity, it's a time capsule. By studying its sluggish activity, scientists can test theories about how black holes grow or don't over cosmic timescales. And one day, when Andromeda's black hole merges with ours billions of years from now, Sagittarius might finally wake up, transforming from a sleeping giant into the most violent engine in the local universe. Until then, it spins quietly in the dark, a reminder that even the most terrifying forces in space sometimes prefer to nap. You'd think galaxies are mostly made of stars, glowing gas, and cosmic dust until you meet the cosmic phantoms like Segway 1, where all that visible stuff barely makes a dent in the total mass. This ultra-faint dwarf galaxy orbiting our Milky Way is a staggering 99.99% dark matter, with its sparse stars acting like accidental ornaments on an invisible monster. Detecting these shadowy giants isn't about spotting starlight, it's about feeling their gravitational handshake. Astronomers first noticed something bizarre when they tracked the motions of Segway 1's handful of stars. They were moving far too fast for the galaxy's meager visible mass to hold them. According to the laws of gravity, those stars should have flung into intergalactic space long ago unless something unseen, something massive, was anchoring them. That something is a halo of dark matter so dense it outweighs everything else in the galaxy by a factor of 1,000. Here's what's even more mind-bending: Segway 1 isn't alone. Galaxies like Triangulum 2 and Draco Dwarf show similar dark matter dominance, their stars practically floating in an ocean of invisible mass. Without dark matter's gravitational glue, these galaxies would have disintegrated billions of years ago. Yet they endure, silent and nearly invisible, their true nature only revealed by the frantic orbits of their few visible stars. Why does this matter? Because these ghostly galaxies are pristine time capsules. Unlike larger galaxies scrambled by collisions and star formation, their dark matter halos remain undisturbed, offering a glimpse into the universe's primordial structure. Some might even be failed galaxies, clumps of dark matter that never gathered enough gas to birth more than a sprinkling of stars. Others could be remnants of ancient building blocks that merged to form galaxies like our Milky Way, their stars stripped away long ago, leaving only their dark skeletons behind. The takeaway is humbling. What we see when we gaze at the cosmos is just the glitter on the surface. Galaxies like Segway 1 remind us that the universe's real architecture is written in darkness, its most powerful forces forever hidden from our eyes. And as telescopes grow more sensitive, we'll likely find more of these shadowy giants, silent, massive, and rewriting the rules of cosmic evolution one invisible halo at a time. Some cosmic events don't just flash and fade, they haunt the universe with ghostly afterimages. When a star explodes as a supernova, the initial blast floods space with searing light, visible across billions of light years. But even after that light fades, the show isn't over. The explosion's energy races outward, slamming into interstellar dust clouds that linger like cosmic chalkboards. These clouds absorb the light, then slowly re-emit it, creating ethereal glows that linger for years, sometimes decades, after the original explosion. Astronomers call these phenomena light echoes, and they're one of space's most mesmerizing sleights of hand. Take supernova 2006 JY, for example. When this star detonated in the galaxy NGC 4258, telescopes captured the initial flash, a brilliant, short-lived spike of light, but then something extraordinary happened. Months later, faint concentric rings began appearing around the explosion site, expanding outward like ripples in a pond. These weren't physical shock waves, they were light echoes, the delayed reflection of the supernova's light bouncing off dust layers at different distances. Each ring corresponded to a separate dust sheet, illuminated in sequence as the light traveled farther into space. It was as if the universe had hit pause on the explosion, replaying it in slow motion across years. What makes light echoes so invaluable to science isn't just their beauty, it's their ability to turn dust clouds into cosmic mirrors. By studying the timing and intensity of these glows, astronomers can reconstruct the original explosion in unprecedented detail, like forensic analysts rewinding a crime scene. They've used echoes to measure supernova energies, map the distribution of interstellar dust, and even catch glimpses of historical stellar explosions that predate telescopes. The most famous example, the light echo of Eta Carinae's 19th century eruption, which still flickers today, offering modern astronomers a window into a cataclysm witnessed by Victorian stargazers. But here's the strangest twist: light echoes can play tricks on time. Because light travels at a fixed speed, dust clouds farther from the explosion take longer to light up. That means what we perceive as a single event might actually be a decades-long tapestry of reflections, each one revealing a different angle of the original blast. In some cases, like supernova 1987A, echoes have revealed previously hidden structures around the star, evidence of violent outbursts that occurred centuries before its final demise. These ghostly glows remind us that the universe doesn't forget. Long after a star's death, its story lingers, written in the delicate interplay of light and shadow. And as telescopes grow more sensitive, they'll capture even fainter echoes, whispers from explosions that occurred before humans even looked up at the sky. Every ripple is a message patiently waiting for us to decode it. Our galaxy's serene spiral might look like a picture of cosmic harmony, but its past is littered with violent conquests. The Milky Way didn't grow by slowly gathering gas and dust. It expanded through galactic cannibalism, swallowing smaller neighbors whole, one of its most famous victims. The Gaia Enceladus dwarf galaxy, a once independent system that met its end around 10 billion years ago in a collision that reshaped our cosmic home forever. Evidence of this ancient feast lies in the odd motions of certain stars. When astronomers analyzed data from the Gaia Space Telescope, they noticed something peculiar: a population of stars orbiting the Milky Way's halo in the opposite direction to the rest, their chemical makeup strikingly different. These stars weren't born here, they were kidnapped. Gaia Enceladus, named for the telescope that exposed its remains, was roughly 1/5 the Milky Way size when it was torn apart. The merger didn't just add stars, it triggered chaos. The violence heated the Milky Way's disk, puffing it into a thicker, more turbulent structure before it settled back into the sleek spiral we know today. But Gaia Enceladus isn't the only victim. The Sagittarius dwarf spheroidal galaxy is currently being ripped apart by the Milky Way's gravity, its stars strewn across our galactic halo like cosmic breadcrumbs. And the Large Magellanic Cloud, it's next on the menu. While it orbits safely for now, simulations show it'll eventually spiral inward, merging with our galaxy in about 2.5 billion years. Each of these collisions leaves a fingerprint: stars with unusual orbits, globular clusters that shouldn't exist here, even ripples in the Milky Way's outer gas. What's fascinating isn't just the destruction, it's the rebirth. Galactic mergers aren't just takedowns, they're catalysts. The influx of fresh gas from devoured galaxies can ignite furious bursts of star formation, while new stellar populations add diversity to the galactic gene pool. Without these ancient collisions, the Milky Way might have remained a boring, petite galaxy, never growing into the grand spiral we call home. So the next time you gaze at the night sky, remember, you're looking at a cosmic battlefield where the quiet glow of stars hides a history of violence, survival, and transformation. The Milky Way isn't just a galaxy, it's a mosaic of conquests, a testament to the universe's relentless drive to build, destroy, and rebuild on the grandest scales imaginable. Most galaxies spin like elegant frisbees, their stars and gas tracing smooth, flat orbits around a central core, but nature loves exceptions. Meet NGC 660, a galaxy so bizarre it looks like a cosmic bullseye, with a ring of stars spinning at a perfect right angle to its main disk. This rare polar ring galaxy defies everything we expect about galactic structure, offering a front-row seat to one of the universe's most dramatic collisions. How does a galaxy end up with such a peculiar shape? The leading theory involves a high-speed galactic heist. Billions of years ago, a smaller galaxy likely sideswiped NGC 660, not head-on but at a sharp angle. The victim galaxy's gas and stars were ripped away by gravity, but instead of scattering into chaos, they settled into a perpendicular orbit, forming a glowing ring that circles the poles like a celestial hula hoop. Picture throwing a pebble into a pond, except in this case, the pond is a galaxy, and the ripples freeze into a permanent, star-studded ring. What's astonishing isn't just the ring's existence, but what it reveals. The gas and stars in these polar rings often have different chemical compositions from the main galaxy, like cosmic fingerprints pointing to their foreign origins. In NGC 660's case, the ring is rich with young, blue stars, suggesting the stolen material reignited star formation long after the collision. These rings act as time capsules, preserving clues about ancient crashes that would otherwise be lost to time. Polar rings aren't just scientific curiosities, they're natural laboratories. Because the rings orbit perpendicular to the galaxy's main disk, astronomers can use them to map the invisible gravitational scaffolding of dark matter that surrounds galaxies. The way the ring twists and moves betrays the shape of the underlying dark matter halo, offering a rare glimpse into the universe's most elusive substance. But the real drama lies in their rarity. Out of millions of catalogued galaxies, fewer than 100 have confirmed polar rings. Most were likely erased by time, their delicate structures disrupted by subsequent collisions or internal turbulence. That makes survivors like NGC 660 cosmic treasures reminders that even in a universe governed by chaos, destruction can sometimes create breathtaking order. Most galaxies cluster together like cosmic cities, bound by gravity in bustling groups, but not every galaxy gets a neighbor. Lost in the vast emptiness of the Boötes void, one of the largest known cosmic deserts, drifts MCG plus 01020015, a spiral galaxy so isolated that if its stars sent out a distress signal today, the light might never reach another galaxy before the universe's end. This isn't just solitude, it's exile on a scale that defies human comprehension. The numbers tell the story. While the average galaxy sits among thousands of others in sprawling clusters, MCG plus 01020015 has nothing. The Boötes void stretches 330 million light-years across, a spherical emptiness so vast you could fit 30 Milky Ways end-to-end in just a fraction of its diameter. Yet within this staggering expanse, fewer than 60 galaxies have been found. That means each one is separated by distances so enormous, they might as well be islands in an endless ocean where the next shore is impossibly out of reach. How does a galaxy end up so alone? The leading theory suggests this void wasn't always empty. Billions of years ago, it might have contained galaxies like any other patch of space. But as the universe expanded, the weaker gravitational pull in this region failed to hold them together. Galaxies either merged into a few massive survivors or drifted outward, drawn toward denser structures beyond the void's edges. MCG plus 01020015 could be one of the last holdouts, a relic from an era before the void consumed its neighbors. What's haunting is the silence. In dense galactic cities, collisions and interactions constantly reshape stars and gas. But here, no passing galaxies stir the spiral's arms, no gravitational encounters trigger bursts of star formation. It spins quietly, its evolution stunted by isolation, like a tree growing alone on a barren plain. Telescopes show its stars are older and redder than those in galactic metropolises, with fewer of the bright blue newborns that light up more social galaxies. Even its hydrogen gas, the raw material for new stars, seems thinner, as if the void itself has leached away its future, yet there's a strange beauty in its loneliness. MCG plus 0102015 is a time capsule, preserving a version of galactic life untouched by the chaos of crowds. While others are twisted by mergers or drained by galactic harassment, this solitary spiral remains pristine, a snapshot of how galaxies might look if the universe had left them undisturbed. It's a reminder that existence doesn't need an audience. Some stories unfold in the dark, written in starlight that might never be seen. In the vast cosmic menagerie, where galaxies come in majestic spirals and hulking ellipticals, there's a quirky outlier that looks like it belongs in a children's book: the Green Pea Galaxy. These tiny, luminous specks, no bigger than a fraction of the Milky Way size, glow with an emerald hue so distinct they were first flagged not by professional astronomers, but by everyday volunteers sifting through images in the Galaxy Zoo project. At first glance, they seemed like glitches, little green misfits in a universe dominated by golds and blues, but the truth turned out to be far more fascinating. What gives these galaxies their peculiar color? It's not some cosmic paint job, it's the telltale signature of oxygen. Green peas are undergoing such explosive star formation that their gas clouds are flooded with ultraviolet light from newborn stars, causing oxygen atoms to fluoresce like neon signs. The effect is so intense that these galaxies outshine their peers in specific wavelengths of green light, standing out like emeralds scattered on black velvet. But the real marvel isn't just their color, it's their sheer productivity. Some green peas churn out stars at rates hundreds of times faster than the Milky Way, packing the fiery birth of countless suns into a space barely larger than a galactic suburb. Their discovery rewrote expectations. Before green peas, astronomers assumed such frenzied starbursts only happened in the early universe or during violent galaxy collisions. Yet here were these unassuming dots thriving in the relatively quiet modern cosmos. Even more surprising, their simplicity. Unlike grand spirals with intricate structures, green peas are often just blobs, compact, chaotic, and unpretentious, like cosmic firecrackers frozen mid-explosion. Their small size and intense activity make them perfect laboratories for studying how galaxies fling open the floodgates of star birth without the drama of mergers or massive black holes. But the real heroes of this story are the citizen scientists who spotted them. Galaxy Zoo's volunteers, clicking through millions of galaxy images, began tagging these green oddities with comments like peas or weird green things, sparking follow-up studies that confirmed their significance. It's a reminder that the universe still holds surprises hiding in plain sight, and sometimes it takes fresh eyes to notice them. Today, green peas are more than curiosities. They're keys to understanding how small galaxies can punch above their weight, igniting stellar fireworks that echo across cosmic time. And somewhere out there, more of these tiny green dynamos are waiting to be found. Their glow a beacon calling to anyone willing to look. For decades, dark matter was considered the invisible scaffolding of the universe, the hidden force that holds galaxies together. Then along came NGC 1052DF2, a galaxy that turned that assumption upside down. Unlike its peers, this ghostly, see-through galaxy appears to have almost no dark matter at all. At first, scientists thought it had to be a mistake. After all, dark matter outweighs visible matter 5-to-1 in most galaxies. How could one exist without it? Yet repeated observations confirmed the impossible. NGC 1052DF2 stars move sluggishly, their speeds matching exactly what you'd expect if only visible matter were pulling the strings. The discovery sent shockwaves through astronomy. Dark matter wasn't just a universal ingredient, it was supposed to be the essential glue binding galaxies. Without it, theorists argued, galaxies like ours would fly apart from their own rotation. So how did NGC 1052DF2 defy the rules? One provocative theory suggests it might be a failed galaxy, born in a region of the early universe where dark matter was unusually scarce. Another idea points to violence, perhaps a catastrophic encounter with a larger galaxy stripped away its dark matter halo, leaving behind only the stars. There's even a fringe hypothesis that dark matter might interact with itself in ways we don't yet understand, creating rare voids where it's absent. The plot thickened when astronomers found more dark matter-deficient galaxies like NGC 1052 and a GC 241905. These outliers aren't just flukes, they're a legitimate population, challenging the idea that dark matter is inseparable from galactic structure. Stranger still, many of these oddballs share traits. They're ultra-diffuse, with stars spread thinly like fog and often orbit near massive galaxies. That proximity hints they might be victims of cosmic theft, their dark matter stolen by a larger neighbor's gravity over billions of years. Yet the controversy isn't settled. Some researchers argue we're misreading the data, that these galaxies do have dark matter, just distributed in unexpected ways. Others propose their unusual star motions could stem from tidal forces or unique formation histories. Each new observation adds twists to the mystery, forcing scientists to question whether dark matter's role is as universal as we thought. What's undeniable is this: galaxies like NGC 1052 are more than cosmic oddities. They're stress tests for our theories, proving that the universe always has a wild card up its sleeve. For every rule we think we've uncovered, there's an exception lurking in the darkness, waiting to rewrite the story. Deep in the heart of the Milky Way, where gravity twists space into knots around our supermassive black hole, astronomers have detected an eerie glow that shouldn't exist, a fountain of antimatter spraying gamma rays across the galactic center. This isn't science fiction. The signature is unmistakable. A spike of light at 511 kilo-electron volts, the exact energy emitted when an electron meets its antimatter twin, a positron, and both vanish in a flash of pure energy. Billions upon billions of these annihilations occur every second near Sagittarius A, creating a gamma-ray haze that blankets the region like an otherworldly aurora. But here's the puzzle: where is all this antimatter coming from? The suspects range from the mundane to the extraordinary. On one hand, dying stars could be the culprits. Certain types of supernova and pulsars are known to produce positrons, and the galactic center is crowded with these stellar corpses. But the numbers don't quite add up. There simply aren't enough of them to explain the sheer volume of antimatter detected. Another possibility involves binary star systems, where a compact object like a neutron star siphons material from its companion, a process that can unleash torrents of positrons. Yet even these cosmic factories seem insufficient to account for the phenomenon's scale and intensity. Then there's the far more tantalizing theory: dark matter. Some models suggest that when hypothetical dark matter particles collide, they could annihilate each other, producing standard particles like electrons and positrons as byproducts. If true, the Milky Way's antimatter glow might be our first tangible clue to dark matter's nature, a fingerprint left by invisible particles smashing together in the darkness. The galactic center, with its dense concentration of dark matter, would be the perfect place for such reactions to occur. It's like stumbling upon a crime scene where the only evidence is the light from an unseen weapon. Yet the mystery deepens when you look at the antimatter's distribution. The gamma rays aren't just clustered around Sagittarius A, they're also spread asymmetrically along the galactic plane, as if sculpted by magnetic fields or stellar winds. Some researchers argue this pattern points to multiple sources, with both dark matter and more conventional astrophysical processes playing a role. Others propose that positrons might be traveling vast distances before annihilating, their paths twisted by the galaxy's tangled magnetic fields. The implications stretch beyond our galaxy. If dark matter is indeed behind this antimatter rain, it could explain similar gamma-ray signals detected in other galaxies, or even the excess positrons measured by satellites like the Alpha Magnetic Spectrometer aboard the International Space Station. Every annihilation event is a tiny echo of the universe's hidden architecture, a whisper from the dark. For now, the antimatter enigma remains unsolved, a cosmic riddle written in gamma rays. But with next-generation telescopes and particle detectors, we're inching closer to an answer. Whether the culprit turns out to be exotic physics or something more mundane, one thing is certain. The heart of our galaxy is far stranger than we ever imagined, a place where matter and antimatter dance on the edge of oblivion, and where the universe's deepest secrets might be hiding in plain sight. Think of the universe as an endless ocean, and galaxies as the swirling eddies within it only. These eddies aren't isolated. They're drawn together into vast, interconnected currents, forming structures so immense they defy comprehension. Enter superclusters, the universe's grandest architectural feats, where galaxies gather not in dozens or hundreds, but in sprawling metropolises of tens of thousands. Our own galactic neighborhood, the Milky Way, is just one tiny resident of the Laniakea supercluster, a celestial titan stretching 520 million light-years across. To put that in perspective, if our galaxy were the size of a grape, Laniakea would be the size of a football stadium. What makes superclusters so extraordinary isn't just their scale, it's their motion. Every galaxy within Laniakea, from the Milky Way to the farthest dwarfs on its edges, is slowly drifting toward a mysterious gravitational anchor known as the Great Attractor. Hidden behind the dusty veil of our own galactic plane, this invisible behemoth, likely a dense knot of dark matter and galaxies, pulls everything in its vicinity like a cosmic whirlpool. The Milky Way, along with every other galaxy in our supercluster, is racing toward it at 14 million miles per hour, caught in a river of galactic motion that will continue for billions of years. But Laniakea isn't unique. The universe is peppered with these gargantuan structures, each a web of galaxy filaments intersecting at dense nodes. The Shapley supercluster, for instance, is even larger than Laniakea, hosting over 8,000 galaxies in a gravitational embrace. These superclusters aren't static, they're dynamic, evolving entities. Over time, their gravitational pull will draw more galaxies into their folds, while dark energy, the mysterious force accelerating the universe's expansion, will eventually tear them apart. It's a cosmic tug of war between gravity's patience and dark energy's relentlessness. What's humbling is realizing that even superclusters aren't the end of the story. They're merely threads in the larger cosmic web, a fractal tapestry where galaxies cluster into groups, groups into clusters, and clusters into superclusters. And beyond that, the web stretches further, hinting at structures so vast we've yet to map them fully. Laniakea, for all its grandeur, might one day be just a footnote in an even grander hierarchy, a reminder that in the universe there's always a bigger picture. In a universe that often feels orderly, where galaxies spin in predictable harmony with their neighbors, nature loves throwing curveballs like NGC 4622, a galaxy that spins defiantly backward. While most galaxies rotate in the same direction as their galactic companions, this spiral rebel whirls the opposite way, a cosmic oddity that defies expectations. The culprit, a violent past. Retrograde rotation like this is often the smoking gun of a chaotic merger, where a smaller galaxy plunged through the disk of its larger neighbor at an odd angle, flipping its spin like a coin tossed into the cosmic void. Picture this: two galaxies approach each other in a gravitational tango. If they collide head-on, their stars and gas might blend into a new, scrambled shape. But if one slips past at a sharp angle, its gravity can act like a cosmic wrench, twisting the larger galaxy's rotation axis or even reversing it entirely. The aftermath is a celestial riddle, a spiral with arms that seem to spiral backward, its stars orbiting in the opposite direction of its neighbors. NGC 4622 isn't alone in this rebellion. Galaxies like NGC 5713 and Messier 64, nicknamed the Black Eye Galaxy, also exhibit this bizarre backward spin, their strange motions betraying ancient collisions lost to time. What's fascinating isn't just the backward spin itself, but what it reveals about galactic resilience. Even after a violent encounter that flips its rotation, a galaxy doesn't tear apart. Gravity holds it together, and over millions of years, the new spin becomes its normal. In some cases, the retrograde motion might even trigger new star formation, as gas clouds slam into each other with extra force, sparking stellar fireworks. The Black Eye Galaxy, for instance, glows with young stars at its core, a testament to the chaos that reshaped it. Yet the mystery deepens when you consider galaxies like NGC 7331, which shows signs of both prograde and retrograde motion in different regions. Here, the outer disk spins opposite the inner disk, like a record playing backward overlaid on one spinning forward. The likely explanation: a smaller galaxy, rich in gas, was absorbed long ago, its material settling into a counter-rotating ring. These galaxies are cosmic palimpsests, their layers of motion preserving a history of mergers and thefts written in the language of spin. For astronomers, retrograde galaxies are more than curiosities, they're forensic evidence. By studying their twists and turns, scientists can reconstruct the violence that shaped them, testing theories about how galaxies grow through collisions. Each backward spin is a timestamp, a clue to the universe's endless game of gravitational billiards. And as telescopes peer deeper into the cosmos, more of these galactic renegades will likely emerge, reminding us that even in the vast, seemingly orderly cosmos, chaos always leaves its mark. Staring at GNZ11 is like looking through a time machine, one that whisks us back to when the universe was a mere 400 million years old. This ancient galaxy, discovered lurking in the constellation Ursa Major, holds the title of oldest known galaxy in the observable cosmos, its light reaching us after a staggering 13.4 billion-year journey. But here's what's truly mind-bending. When we observe GNZ11, we're not seeing it as it exists today. We're witnessing its infancy, a snapshot of a galaxy still taking its first cosmic breaths in a universe still warm from the Big Bang. What makes GNZ11 so extraordinary isn't just its age, it's the sheer audacity of its existence. The early universe was a chaotic, cramped place, filled with swirling hot gas and the afterglow of creation. Conventional wisdom suggested galaxies needed billions of years to assemble, yet GNZ11 defies that logic. Despite the universe's youth, it's already a fully formed galaxy, brimming with stars and radiating intense ultraviolet light. The James Webb Space Telescope's piercing infrared vision has revealed details invisible to earlier observatories, clusters of massive blue stars, far hotter and brighter than our Sun, burning furiously in a cosmos barely out of its cradle. How did GNZ11 grow so large so fast? One theory points to a head start dark matter clumps that formed earlier than expected, pulling in gas with unusual efficiency. Another possibility is that the first stars were monsters, hundreds of times more massive than our Sun, living fast and dying in cataclysmic explosions that seeded the galaxy with heavy elements at breakneck speed. JWST spectroscopic studies have detected traces of oxygen and nitrogen in GNZ11, elements forged in those early stellar furnaces. These atoms shouldn't have existed in such abundance so soon, yet there they are, fingerprints of a generation of stars that lived and died before the galaxy was even a billion years old. But GNZ11 isn't just a relic, it's a Rosetta Stone. By studying its light, astronomers can decode the conditions of the early universe. The galaxy's ultraviolet glow, for instance, hints at how the cosmic fog of neutral hydrogen was being burned away by the first starlight, a process called reionization. It's like finding a fossilized campfire that helped melt the ice age, a tiny beacon that rewrote the entire landscape around it. And with JWST unmatched sensitivity, scientists are now uncovering even older galaxies, pushing the frontier of cosmic dawn closer to the Big Bang itself. What's humbling is realizing GNZ 11 might not hold its record forever. As telescopes peer deeper, they're finding galaxies that existed even earlier, each one rewriting the timeline of cosmic evolution. But for now, this ancient pioneer stands as a testament to the universe's relentless creativity, proof that even in its earliest moments, it was already building wonders beyond our imagination. Most galaxies fit neatly into categories: spirals, ellipticals, irregulars, but some defy the cosmic dress code entirely. Take LEDA 36252, a galaxy stretched into the shape of a celestial tadpole, its bulbous head crammed with stars and a wispy tail of gas trailing behind like a cosmic afterthought. This isn't just a quirk of perspective. It's the aftermath of a galactic drama where either a violent collision or relentless cosmic winds sculpted a perfectly ordinary galaxy into this bizarre, lopsided form. How does a galaxy end up looking like it's swimming through space? The leading theory points to ram pressure stripping, a process as brutal as it sounds. When a galaxy plows through the superheated gas filling a galaxy cluster, the intense pressure acts like a hurricane wind, ripping away its loose gas and dust. The galaxy's stars, bound tight by gravity, hold their ground, but the lighter gas gets swept backward, forming that iconic tail. Imagine running through a rainstorm with a balloon. The balloon, your gas, gets tugged behind you, while you, the stars, keep moving forward. That's LEDA 36252's life story, a lone traveler fighting the cosmic currents. Yet collisions can create similar shapes. If two galaxies graze each other at just the right angle, their gravitational tug of war can stretch one into a tadpole with the head packed with stolen stars and the tail littered with debris. The antennae galaxies, for instance, are mid-collision, their long, streamer-like tails proof of the chaos. But unlike LEDA 36252, their fate is merger, not isolation. Tadpole galaxies, by contrast, often stay deformed, their tails fading over billions of years as the gas disperses or gets absorbed by larger neighbors. What's fascinating about these cosmic oddities isn't just their shape, it's the clues they hold. The length and composition of a tadpole's tail can reveal the speed and direction of its journey, like a galactic contrail. Some tails even harbor pockets of star formation, where the displaced gas collapses into new suns, turning the tail into a nursery against the void. And because tadpole galaxies are rare, making up less than 1% of known galaxies, each one is a precious snapshot of the extreme forces shaping the universe. LEDA 36252 might look like a misfit, but it's a testament to the universe's creativity. Whether sculpted by wind or collision, it reminds us that galaxies aren't static paintings, they're dynamic sculptures, forever being reshaped by the invisible hands of physics. And somewhere out there, another tadpole is drifting, its tail glowing faintly with the story of its journey. Among the countless galaxies swirling through the cosmos, there's one with a unique connection to our Milky Way, not just a distant cousin, but a long-lost sibling. Meet CGCG 137068, a spiral galaxy so similar to ours it's like peering into a cosmic mirror. This celestial twin didn't just form under comparable conditions, it literally shared a nursery with us, born from the same primordial gas cloud over 13 billion years ago before the tides of cosmic expansion pulled us apart. What makes this discovery so profound is the rarity of tracing galactic lineages. Most galaxies form from scattered pockets of gas, their origins lost to time. But CGCG 137068 carries chemical fingerprints that unmistakably link it to the Milky Way. Identical ratios of heavy elements like oxygen, neon, and sulfur, forged in the same stellar furnaces during their shared infancy. Think of it like two siblings separated at birth, their DNA telling a story no amount of time could erase. While our galaxy grew into its majestic spiral, its sibling drifted nearly 100 million light-years away, evolving in isolation yet retaining that primordial kinship in its stars. The implications stretch far beyond sentimentality. By studying this galactic sibling, astronomers can piece together the Milky Way's own chaotic childhood. CGCG 137068's current structure, its star formation patterns, the distribution of its globular clusters, even the activity of its central black hole, serves as a control group, revealing how much of our galaxy's evolution was shaped by its environment versus its innate blueprint. Had it not been for random gravitational nudges in the early universe, we might have grown up side by side, two spirals spinning in tandem, yet the differences are just as telling. While the Milky Way has cannibalized smaller galaxies to bulk up, its sibling appears more solitary, its spiral arms less distorted by violent mergers. Without the Sagittarius dwarf or the impending collision with Andromeda to stir the pot, CGCG 137068 offers a glimpse of what our galaxy might have looked like had it matured in quiet solitude. Its stars are slightly older on average, its gas reservoirs less depleted. A version of the Milky Way frozen in a quieter timeline. This cosmic reunion isn't just about the past, it's a window into galactic destiny. As both galaxies continue to drift apart, tugged by dark energy's inexorable push, their fates will diverge completely. One day, CGCG 137068 will vanish beyond the observable universe's edge, its light stretched too far to detect. But for now, it remains a silent witness to our shared origin, a reminder that even in the vastness of space, nothing, not even a galaxy, is truly alone. Most galaxies hide a simple secret at their hearts, a dense core where stars crowd together like commuters at rush hour. But every now and then, astronomers stumble upon something far more peculiar. A galaxy with an X-shaped core, its center splashed with luminous arms that form a perfect cosmic X. NGC 5866, a lenticular galaxy 44 million light-years away, is one of these celestial enigmas, its nucleus crisscrossed with glowing filaments that defy the usual rules of galactic architecture. So how does a galaxy end up with such a striking center? One leading theory points to a high-stakes gravitational tango between two supermassive black holes. When galaxies merge, their central black holes eventually spiral toward each other, warping the surrounding stars and gas into chaotic orbits. If the black holes don't collide head-on but instead swing past each other at an angle, their gravitational pull can sculpt the galaxy's core into an X shape, like two invisible hands kneading cosmic dough from different directions. The result, a pair of intersecting stellar streams glowing faintly as they stretch into space. But black holes aren't the only possible sculptors. Another explanation involves something far quieter, a tilted dust ring. In galaxies like NGC 5866, thick disks of gas and dust orbit the core at sharp angles to the main galactic plane. When starlight shines through this lopsided ring, it casts shadows and highlights that appear as an X when viewed edge-on from Earth. It's the galactic equivalent of holding a vinyl record at an angle under a lamp. The grooves catch the light just right to form a crosshatch pattern. What's fascinating is that these X-shaped cores aren't just aesthetic oddities, they're forensic evidence. The angle and sharpness of the X's arms can reveal the violence or lack thereof in a galaxy's past. A crisp, symmetrical X might suggest a relatively orderly merger, while a messy, asymmetrical one could hint at a chaotic collision with multiple galaxies. And then there's the mystery of persistence. Some X-shaped cores, like NGC 5866's, have maintained their structure for billions of years, resisting the gravitational pull of neighboring stars and dark matter that should have blurred them into oblivion. Perhaps the most tantalizing detail is what these X's leave unsaid. For every one we've spotted, there are likely dozens more hiding in plain sight. their telltale crosses too faint or too edge-on for our telescopes to catch. They remind us that even in something as familiar as a galaxy's heart, the universe loves to hide its wildest designs, waiting for the right moment and the right observer to bring them into the light. Magnetic fields might seem like the sort of thing that only affect planets or stars, but the universe loves to upend expectations. Stretching between galaxies across unfathomable voids where even gravity's grasp weakens, are the largest magnetic structures ever detected. Cosmic filaments of force so vast they could thread entire galaxy clusters together like beads on an invisible string. These aren't the delicate, localized fields we see around pulsars or black holes. They're titanic, weaving through intergalactic space for millions of light years, their origins as mysterious as their scale. Take the bridge between the galaxy clusters Able 399 and Able 401, for instance. Separated by 10 million light-years of near-nothingness, these colossal gatherings of galaxies shouldn't have much to do with each other. Yet radio telescopes have revealed a faint but unmistakable glow, synchrotron radiation betraying the presence of relativistic electrons spiraling along magnetic field lines. Somehow, those lines span the entire gap, a highway of magnetism with no obvious source. One theory suggests these fields might be relics from the universe's infancy, stretched to cosmic proportions during the Big Bang's expansion, like invisible ink smeared across the fabric of space-time. Others propose they're dynamos fueled by galactic turbulence, where the motion of charged particles in galaxy clusters acts like a universe-sized generator, amplifying weak seed fields over billions of years. What's wild is how these fields shape the cosmos in ways we're only beginning to grasp. Charged particles traveling through them don't just move in straight lines, they twist and spiral, potentially redirecting the paths of cosmic rays that would otherwise pepper planets unchecked. Some researchers speculate these filaments could even influence how galaxy clusters evolve, their magnetic pressure subtly resisting gravity's pull or guiding the flow of hot gas between clusters. It's a reminder that the universe isn't just held together by gravity, it's also stitched with invisible threads of force, a tapestry of magnetism we've only just learned to see. And here's the kicker, we're likely underestimating their scale. Current instruments can only detect the strongest intergalactic fields, leaving weaker ones invisible. Future telescopes like the Square Kilometre Array might reveal a cosmos far more magnetized than we ever imagined, with every filament of the cosmic web crackling with unseen energy. Until then, these ghostly giants linger at the edge of detection, silent, colossal, and rewriting the rules of what we thought we knew about the empty spaces between the stars. Some galaxies don't just fade quietly into cosmic history, they flicker like dying light bulbs, vanishing and reappearing on timescales that baffle astronomers. Take Markarian 1018, a galaxy that once blazed as brilliantly as a quasar, then dimmed to near invisibility, only to flare up again decades later. This isn't just random cosmic weather, it's the signature of a supermassive black hole with an erratic appetite, cycling between feasting and fasting in ways that rewrite our understanding of how galaxies evolve. At its peak, Markarian 1018's core outshone its entire galaxy by a factor of 100, a beacon visible across billions of light years. Then, in the span of just a few years, its brightness plummeted by a factor of 10. Telescopes watching this transformation saw the equivalent of a stadium floodlight shrinking to a candle flame, not over millennia but within a human lifetime. The culprit, a black hole that suddenly went on a diet. Most supermassive black holes consume gas at a steady, if voracious, rate. But in galaxies like Markarian 1018, something disrupts the flow, perhaps a stellar flyby, nudging gas away from the black hole's maw, or turbulence in the surrounding disk cutting off its meal mid-bite. What's eerie is how quickly the galaxy's personality changes. When the black hole feeds, ionized gas swirls in frenzied orbits, emitting blinding radiation. When it starves, the gas cools and settles into a quieter state, and the galaxy's core dims to a faint smudge. This isn't a one-time event either. Markarian 1018 has cycled through multiple bright and dim phases over decades, making it a cosmic chameleon. Other galaxies, like NGC 7603, show similar behavior, flickering unpredictably as if controlled by a celestial switch. The real mystery lies in what triggers these transitions. One theory suggests that dual black holes might be at play, their gravitational tugs disrupting gas flows like dueling whirlpools. Another idea points to instabilities in the accretion disk. Imagine a record skipping, momentarily cutting off the music before resuming. Even stranger, some of these ghost quasars might be victims of their own success. Radiation from their feeding black holes could blow away nearby gas, starving themselves until fresh material drifts back into reach. These flickering giants aren't just curiosities, they're cosmic laboratories. By studying them, astronomers can test theories about black hole growth and feedback, processes that shape entire galaxies. And they hint at a universe far more dynamic than we ever imagined, where even the mightiest engines of light can vanish and return like ghosts stepping in and out of the shadows. At the heart of certain galaxies, cosmic pressure cookers are at work, not just forming stars, but blowing bubbles on scales so vast they could swallow our entire solar system without a trace. NGC 3079, a starburst galaxy 50 million light-years away, is one such celestial soap blower where ferocious stellar winds have inflated twin bubbles of superheated gas that stretch 2,500 light-years from end to end. These aren't the delicate spheres you'd see floating in a child's hands. These are roiling, million-degree infernos, their surfaces rippling with shockwaves as they expand into the void like cosmic balloons caught mid-pop. What forces could possibly create structures this enormous? The answer lies in the galaxy's frenzied core, where clusters of massive stars live fast and die young. Each of these stellar powerhouses burns through its fuel in just millions of years, a blink in cosmic time before exploding as supernova. But before they perish, they unleash torrents of radiation and charged particles, stellar winds screaming outward at thousands of miles per second. When hundreds of these stars cluster together, their combined fury acts like a galactic leaf blower, carving out cavities in the surrounding gas and sculpting them into these colossal bubbles. The process isn't gentle. As the bubbles grow, they slam into cooler gas clouds, triggering secondary shockwaves that glow in X-rays, a telltale signature caught by telescopes like Chandra. Yet NGC 3079's bubbles aren't just spectacular, they're galactic engines. The same violent processes that create them also inject heavy elements, carbon, oxygen, iron, into intergalactic space, seeding future generations of stars and planets. Even more striking, the bubble's expansion can regulate star formation itself. By ejecting gas from the galaxy's core, they starve younger stellar nurseries of raw material, effectively putting a cosmic lid on how many new stars can form. It's a self-limiting cycle. Too much star birth leads to bubbles, and bubbles stifle further star birth. Other galaxies take this phenomenon to extremes. In the nearby Large Magellanic Cloud, the Tarantula Nebula hosts a bubble called Superbubble 30 Doradus C, where overlapping supernova have created a structure so energetic it accelerates particles to near light speed, making it one of the brightest sources of gamma rays in the local universe. And in distant quasars, supermassive black holes can inflate bubbles hundreds of thousands of light-years wide, their jets punching through galactic gas like a needle through fabric. But what makes these structures truly humbling is their ephemeral nature. Unlike the galaxies that birth them, most bubbles last only tens of millions of years before dissipating, their gas cooling, their shockwaves fading, their energy absorbed by the cosmic medium. They're fleeting masterpieces, cosmic street art painted in plasma and radiation, visible only until the next stellar storm scrubs them away. Yet in their brief lives, they transform their surroundings, proving that even the most transient phenomena can leave echoes that shape the universe for eons. The Milky Way isn't just home to planets neatly orbiting stars, it's teeming with cosmic drifters, rogue worlds untethered from any solar system, wandering the darkness alone. Astronomers estimate there could be billions of these nomads adrift in our galaxy, outnumbering stars by as much as 20 to 1. Picture Earth ripped from the sun's embrace, hurled into the void by some ancient gravitational catastrophe, doomed to drift forever in perpetual night. That's the reality for countless rogue planets, their origins as dramatic as their fates are desolate. How does a planet get exiled from its home? The most common culprit is gravitational chaos. Young star systems are violent neighborhoods, especially where multiple giant planets jostle for space. When these massive worlds pass too close to one another, their gravitational tug of war can fling smaller planets outward at blistering speeds like a cosmic slingshot, firing them into interstellar space. Some simulations suggest a single unstable system could eject dozens of planets over its lifetime, scattering them like seeds in the galactic wind. Other rogue worlds might form directly from collapsing gas clouds, born free without ever knowing the warmth of a parent star. Detecting these lonely wanderers is a monumental challenge. Without starlight to illuminate them, they're nearly invisible. Only the faintest glow of residual heat betrays their presence. But astronomers have tricks. Occasionally, a rogue planet's gravity bends the light of a distant star as it passes in front, a phenomenon called microlensing. These fleeting events, lasting mere hours, have revealed planets as small as Mars floating untethered in the abyss. Other rogues are spotted by their infrared signatures, like the free-floating planetary mass object CFBDS IR2149 in the TW Hydra Association, glowing dimly with the fading warmth of its birth. The implications are staggering. Imagine a rogue planet with a subsurface ocean, ejected during its system's turbulent youth but still harboring liquid water thanks to geothermal heat or insulating ice. Could life cling on in such extreme isolation? Some astrobiologists speculate these dark worlds might be far more common habitats than Earth-like planets, their icy shells shielding ecosystems from cosmic radiation. Others envision rogue planets as future way stations for interstellar travel, dark, frozen pit stops where civilizations could mine resources or rest during centuries-long voyages between stars. What's certain is this: the galaxy's true planetary population dwarfs what we see orbiting stars. For every familiar world like Jupiter or Saturn, there could be a dozen more drifting unseen, their existence a testament to the universe's boundless capacity for both creation and abandonment. They remind us that stability is the exception, not the rule, and that even in the cosmic vastness, nothing, not even a planet, is guaranteed a place to call home. From galactic cannibals to invisible dark matter behemoths, rogue hypervelocity stars to flickering quasars, we've journeyed through the universe's strangest corners, and still, galaxies keep rewriting the rules. Just think, we live in a reality where black holes sculpt entire galaxies, where cosmic tadpoles swim through voids, and where galaxies spin backward like cosmic contrarians. Every time we think we've got the universe figured out, it throws another curveball like the antimatter geyser at our galaxy's heart, or the Milky Way's long-lost twin drifting millions of light years away. What's wildest isn't just the scale of these discoveries, it's how recent so many of them are. A century ago, we didn't even know other galaxies existed beyond the Milky Way. Now we're finding ghostly dark matter galaxies, galaxies that flicker like dying light bulbs, and even ones shaped like celestial pretzels. The more we look, the more we realize how much we've underestimated the universe's creativity. So here's the real question: which fact shattered your cosmic expectations? Was it learning that most galaxies are just glitter on an ocean of dark matter? Or that our Milky Way will one day merge with Andromeda in a slow-motion ballet where stars almost never collide? Maybe it was the mind-bending idea that rogue planets outnumber stars, drifting like cosmic orphans through the void. Drop a comment below. We want to hear which revelation left you staring at the night sky with fresh awe. And if you're hungry for more cosmic mysteries, don't forget to hit subscribe. The universe isn't done surprising us. With every new telescope, every deeper peek into the void, we're uncovering truth stranger than fiction. And you'll want a front row seat for the next jaw-dropping discovery. Until then, keep looking up. The cosmos has a way of reminding us that reality, even at its most familiar, is anything but ordinary.